We'll come back. Topic 7. Boundary layer, convection, and approximate solutions. An introduction. A. Let's review what we know about boundary layer. First, when a cold flow is passing over a hot stationary plate, we could have velocity boundary layer developed, thermal boundary layer developed, and both boundary layers can be developed on the same surface. Second, boundary layer is a high Reynolds number phenomenon. That is, if the Reynolds number is small, like less than 1000, there's no boundary layer formed. Third, the boundary layer can not only be developed on the surface of slender bodies, but also on the surface of blunt bodies and on the internal flow surface. Lastly, within the boundary layer, the velocity and temperature vary dramatically in the y direction. As a result, the friction and convection heat rate are very significant within the boundary layer. On the other hand, outside of the boundary layer, there's almost no friction or convection. Therefore, the Bernoulli's equation and Euler's equation can be applied. B. Boundary layer can be developed on a solid surface. The flow can be all smooth laminar, over all chaotic turbulent, or a mixed smooth laminar flow, transition, and chaotic turbulent. C. We often see that boundary layer is thin. How thin it is? Let's do a simple calculation by using the boundary layer thickness equation 1 and 2 for laminar flow and turbulent flow respectively. Assume the fluid is air. The length is 1 meter. We have two separate velocities. One is faster, the other is slower, so that we have one flow which is turbulent, the other flow which is laminar. By plugging numbers to the equation 1 and 2, we get the laminar boundary layer thickness, which is 1 centimeter, and turbulent boundary layer thickness, which is 2 centimeter. Compare to the length x equal 1 meter value, the boundary layer thickness for both laminar flow and turbulent flow are small. Therefore, we draw the conclusion that if the Reynolds number is large, boundary layer is formed on the top of the solid surface, and its thickness compared to the length is small. This characteristic will be used to simplify the governing equation, the boundary layer approximation and equations. First, the boundary layer approximation states that for velocity boundary layer, the velocity in the x direction is much greater than the velocity in the y direction. The derivative in y direction of x direction velocity is much greater than other derivatives. For thermal boundary layer, the derivative in the y direction is much greater than the derivative in the x direction. Second, this is our governing equations: continuity, momentum, energy, under the condition that two-dimensional in the x and the y direction, a steady, no gravity, no internal energy generation, neglecting the viscous dissipation. Next, we will apply the boundary layer approximation to simplify the governing equations to generate a boundary layer equations. We will keep the continuity equation, never drop any term in this mass conservation. 2, we drop the smallest term according to the boundary layer approximation to give the x direction momentum equation. 2, 3, drop all the small terms in the y direction momentum equation to give equation 3. It indicates that along the boundary layer thickness direction, which is y direction, the pressure has no change. 4, we drop the smallest term according to the boundary layer approximation to give equation 4. This is our boundary layer equations. The question is, do we have a unique solution from the boundary layer equations? The answer is yes. We have 3 equations and 3 unknowns: velocity u, v, and the temperature T. The problem is closed. However, by checking, it is noticed that the 3 equations are still partial differential equation. Therefore, we will turn to similarity method to get exact solution for very simple laminar flow over a simple geometry, the plate. For laminar and turbulent boundary layer flow, we turn to a unical method to get approximate solution. For advanced problems, we turn to numerical method to get approximate solution by coupling the boundary layer solution with the outside inviscid flow solution. Next, we'll introduce the integral method by focusing on its idea. F. Von Karman integral method. First, for these three curves, the integration, which is the area and the curve, will provide the same result. You can think of the integration as work, which is integrate pressure time the volume. Even though the shape are so different for these three curves. This would indicate that integration has this uniqueness. That is, it tolerates the change in the shape. This idea was borrowed and applied by von Karman to obtain the friction and convection heat rate. Let's find out how. First, we assume a rough velocity and temperature profile like the curve, which satisfy the proper boundary conditions. For example, we use sine function to approximate the velocity profile. We use the polynomial to approximate the temperature profile. Second, since we know the velocity in the x direction, we will integrate the continuity equation from 0 to the thickness of the velocity boundary layer, and finally to get the velocity in the y direction. Third, we turn to our energy equation by integrating it from 0 to the thickness of a thermal boundary layer, delta T. Equation is our energy equation. We break the second derivative into two first derivative. Next, we do the integration on the left hand side and the right hand side. Then, by comparing with the Fourier law, this term is replaced by the heat flux, and eventually we will get the convection heat flux because we assumed the velocity profile, temperature profile, and we obtained the velocity profile in the y direction from the continuity equation. from this introduction of the idea using the integral method, you can see it is very clever to use the approximation of a velocity and temperature profile to get desired friction and convection heat rate, but this process avoids solving the partial differential equation. At this point, we covered topic 7. You're expected to answer the question 1, 2, and 3. Since it is an introduction, what we did not cover is boundary layer theory, boundary layer and aerodynamics, a lot about drags and lift. 3, numerical methods. 4, a turbulent boundary layer, including the mean velocity profile near the wall, and boundary layer equation, averaged equation, and its solution strategy. It is left for the future study. At this point, we finished Advanced Convection Part 2 with beautiful summary and outcomes in terms of concept, variables, skills, equations, and it ends the Advanced Convection Part 2.